Hi, welcome back to Educator.com. Today we're going to be talking about polymers. The way you make a polymer, one way to make a polymer, is to start with a single unit. We call that a monomer. In this case, this is vinyl chloride. And if you imagine that this monomer reacts with another, and then that reacts with another, and so on, we can build up a dimer, and then a trimer, and so on, until finally we have a polymer, many repeating units. And so this is an example of a polymer. Because the monomer is known as vinyl chloride, this polymer is called polyvinyl chloride, or PVC. This is a real common polymer that you may have heard of. And where we find polymers in our everyday lives are, for example, all the plastics that we have all around us. Those are examples of polymers. Now, not all polymers are all carbon chains like this. We'll see that there are other polymers as well. But we have thousands of repeating units, tens of thousands of units. And depending on what these groups are hanging off of the polymer chain, it's going to dramatically affect the properties of our polymer and therefore affect their uses and what kinds of materials we can use from them. Now notice I put a bracket around here. This is showing the repeating unit. It has a chlorine and two carbons and a chlorine and two carbons. So one thing we can do when we look at a polymer is try and identify what the monomer component is and what is the repeating unit that goes on through the polymer. Now, how do polymers act? What are their properties like? Well, they're very long chains, and so if you have them in liquid form, those long chains tend to get tangled up. They don't flow very easily. So as a liquid, the polymer solutions are kind of thick or gooey or sticky. Things that you have those kinds of properties usually have some kind of polymer involved with them. Okay, as a solid, depending on the polymer, you can have ones that are very flexible or spongy and pliable, others that are rigid and very durable. They can be transparent, and we have plastics that we use for those, or they can be opaque. And what we find is a very wide range of properties, so we end up with very useful materials. And again, the chain lengths will vary of a given polymer. There'll be varying lengths, but our molecular weights can range anywhere from like 10,000 to 1,000,000 grams per mole. So these are just huge molecules, extremely long carbon chains, not necessarily carbon chains. Now, nature provides some polymers. For example, rubber comes from the rubber tree. If you make a cut on the bark of the tree as a defense mechanism, it produces this rubber, and so you can tap into that just like you would tap into like a maple tree to get maple syrup. You could tap into that and collect the rubber, and that material is useful because it's waterproof, so it could be used for waterproofing, and that's what it was used many years ago. But if we tried to use it, and here's the structure of it. So the way rubber is made is we could take this isoprene unit. It's a 5-carbon diene. That's the monomer, and when this forms a chain, here we see our 5-carbon monomer again, and this is the structure of natural rubber. It has the Z configuration, like the cis alkene here of those two high priority groups are in the Z configuration. That's what natural rubber looks like. Now, if we think of rubber like a rubber band, we know we can stretch that and it goes back to its original shape. Well, natural rubber doesn't do that. The sheets, the polymer chains, if you tear at them, they'll just tear apart. There's nothing holding them together. But in 1839, Charles Goodyear discovered that he could do a process called vulcanization, where he could modify the rubber by reacting with sulfur. And what's formed here are disulfide cross-linking. We get these bridges. You can see now that some of the double bonds used to be repeating double bonds. Well, some of the double bonds have been reacted and have added the disulfide bridge. And what that does is it holds one polymer chain, holds them all together. And so now we can stretch it and it'll conform to its original shape. We describe such polymers as elastomers, ones that are capable of being stretched and will come back. So that's what we recognize as things like rubber band, rubber that we use in our everyday lives. Now, you might recognize the name Goodyear because that's who created Goodyear tires, and so this is the material that was used for tires and other things that we use rubber for these days. Polysaccharides are another example of natural polymers. This is when we have saccharides, sugars, linked together in very, very long chains. A couple examples of that, starch and cellulose. Starch, these are all glucose units in both of these. In fact, I just noticed there's a typo. Sorry about that. These are all glucose units. If the glucose units are hooked together where this oxygen, this glycosidic bond is pointing down, that's the alpha linkage. That's what we know as starch. That's the polymer that's found in potatoes, wheat, corn, rice, the things we know as kind of starchy materials. And we use that starch in cooking as a thickening agent to make sauces and gravies thicker and so on. There's some branching that can occur here. It's a branch structure as well. And cellulose is the structure when glucose has this glycosidic bond where this oxygen is pointing in the up direction, the beta linkage. Cellulose is what's used for cell walls, so we can use that material for making paper or cotton or cardboard or something like that. So there are natural polymers that are used for materials as well. Some other examples of natural polymers include proteins. So a protein is what we get when we take an amino acid and we link it together as an amide. So an amino acid has this was a carboxylic acid, this was an amine, and then they hook together as this amide linkage. And these R groups vary depending on what amino acids you've used. So again, proteins can have a very wide variety of structures, and they're not necessarily a single monomer because every amino acid can be different. But again, we have these repeating units and very long chains, so that's why we describe them as a polymer. And certain proteins also can be used for materials, for structural things that nature builds. For example, keratin is a protein that's used for hair. It's used to build horns, fingernails, claws, the scales that are in snakes and bird feathers, turtle shells. So that's used in a wide variety of natural materials, some usually pretty durable materials. And finally, DNA strands are also examples of polymers. A DNA strand has a sugar phosphate backbone, and again, it varies. We don't have identical monomer units because the base, this is a ribose sugar or a deoxyribose sugar, depending on whether it's RNA or DNA. And the bases that we have here vary. We could have adenosine or thymine or so on. And it's those bases that hydrogen bond with other bases, and that's how we get the double-stranded DNA that goes to the helical shape and so on. So this is also a polymer that has sugar and phosphate as its backbone there. Now, the way you can observe DNA as a polymer is you can search on YouTube for some videos on how to isolate DNA from strawberries or from bananas. It's a real easy experiment you could do at home where you denature the cell, or you break down the cells, and then you can pull out these really, really long strands, this stringy material, and that's actually the DNA. You can see really, really long strands of the DNA that you can isolate. It's kind of a cool experiment to try. So nature does provide us with certain polymers, but where it's really come into our everyday lives and really made improved our lives through chemistry are looking at synthetic polymers. So that's where we develop polymers in the lab. Now this was actually an accidental discovery in 1933 at the Imperial Chemical Industries company in Great Britain. And what a chemist did there was he took a gas like ethylene. I think he had the fluorinated version, tetrafluoroethylene, and he had it in a cylinder, a high pressure, amount of it in cylinder, put it under high pressure, and he was going to use it for something. But when he let it sit overnight, he realized that in the morning he looked at the pressure gauge and there was no pressure left in the cylinder. But the cylinder still weighed the same amount it did when it was full. So the material was still there. It was just no longer a gas. So he opened up the cylinder and found a powder in there instead of the gas. And so he had discovered that accidentally that this gas had polymerized, had formed this long chains and made this material. Now, when he did the fluorinated version of that, so there were fluorines in all these positions instead of hydrogens, and what he discovered was Teflon. And he tested this new material and found that it was unreactive, it wouldn't dissolve anything, wouldn't react with anything, you couldn't burn it. And so, what do you do with this? But it turned out it had really cool applications. What we use Teflon for, related materials, are non-stick surfaces. So if we coat our cookware with that, it's very easy to cook and things don't stick to it. So, so that was one example of one of the polymers that we use today. If we use ethylene, if we look at the simplest polymer here, ethylene, where all it is a 2-carbon chain, when it bonds together, we call that polyethylene. Now again, this was discovered in the 1930s, and shortly thereafter, some commercial uses were developed for it because it's very lightweight and it's hydrophobic. It was found it could be a very good insulator. So by 1938, it was used to coat a telephone cable so that it could be laid underwater. That was the first time they were ever able to do that because they didn't have a suitable material to waterproof it. When World War II came around, they were able to, using polyethylene, the plastic cases, they were able to use that as an insulator around their radar units and radar devices, and they were able to install those in airplanes for the first time. So radar is used to locate where submarines are under the water, and the British forces were able to install those in their aircraft for the first time ever. So they were able to take out all of the enemy subs, and that was a huge advantage in the war and really made a big difference in their success in World War II. It turns out that it's a great insulator. It's also can be made to be flexible and airtight. So in 1948, Earl Tupper from DuPont found some good uses for it, and you might recognize something like this. This is Tupperware. So we could have flexible things that can keep out air and keep it airtight. So when it came to food storage, this really was a huge turning point and really revolutionized the way we were able to keep our food safe and keep it lasting longer thanks to plastic food storage. And that's just the tip of the iceberg. Really, there's so many more polymers, and just a few examples of that. So we talked about polyethylene. So that's we saw some of the applications of that for like Tupperware. It's also what you have for plastic bags, Ziploc bags, those sorts of things. So it's flexible and see-through and that kind of thing. Glad wrap, some of the wraps that we have that we can put food in as well.